All right, I'd like to begin by thanking the organizers for inviting me to come talk to you today. Thank you, David and Professor Casati. So the organizers asked me to give a tutorial lecture about charge and heat transport, and particularly in the context of engine design. And so that's what I prepared for you today. The talk, I'm going to give some motivation of my talk. It's going to have some overlap with some of the earlier talks in the first day of this session. And some of the things I'll be talking about also came up on Tuesday and a little bit on Wednesday as well. So hopefully, if I go over some of the same material, it won't be too bad. Good. So the outline is I want to start with some motivation about why we should study thermoelectricity and mesoscopic structures. I'll be talking a little bit about the history of this, some of the interesting historical developments about what prompted some of the big ideas behind this field. I'm going to talk about some fundamental concepts. So I promised you in the title slide, we'll be talking about how to design these engines. So I'm going to talk about what basic fundamental principles, what ingredients do we need to make such an engine, and then I'm going to give you several examples. So we're going to walk through a series of these examples using a particular mesoscopic engine as a kind of paradigmatic example to illustrate these design principles, and then trying to think about optimizing certain quantities like thermodynamic efficiency, or efficiency at maximum power, or what have you, and then talking about if you wanted to take these things from some proof of principle design and you're sitting in your dilution refrigerator and want to make them actually into some kind of practical device that might be useful for someone, how might you go about doing that? So we'll talk a little bit about that. Fortunately, one of the great things about this field is that there are now several experiments dealing with this kind of physics. And so I'll talk you through some of the experiments and how those have borne out some of the theoretical predictions, and then give some outlook then on what that means for the future of this field. And then what I want to end with is I want to sort of think about my vision for what we're going to be doing going forward, talking about not just quantum thermal engines, but fully quantum engines. So right now our resource that we've been dealing with almost the entire conference has been about a thermal reservoir, taking heat from a hot reservoir to a cold air reservoir. And this is, of course, a very useful technique, but it's a very crude technique as well. It's something that you know, the cavemen might be able to appreciate about using this resource. Well, Terry's a little skeptical, but okay. But I want to talk about can we push this idea and go further in talking about other kinds of quantum resources besides just thermal quantum resources. All right. I want to also kick this off by saying that the fun does not end at the end of this conference, but we go on next month. We have another conference that I'm organizing with my co-organizers here in Santa Barbara, California, and so we'll be there for 6 weeks working on these topics. So there's both good news and bad news about this conference. The good news is that it turns out that it was extremely popular. That we got lots and lots of applications to come and work on this subject. And so I'm really excited about the kinds of opportunities we'll have next month, along with the conference. The bad news is that there were lots and lots of people that were interested in this, and so consequently we couldn't take everyone because the KITP gave us an upper cutoff. So if you wanted to come and couldn't, I apologize for that. There just wasn't enough room to accommodate all the good people that wanted to be there. So anyway, so I'll see many of you here there in Santa Barbara next month. Okay, so I want to begin just before I forget to thank my collaborators. I've been working on this subject. I think I started working on the subject about 6 years ago. I'm on sabbatical now from my University of Rochester position in California. On my last sabbatical, I came to Geneva and we started working with Marcus on some of these ideas. And that's really what got me started in working on this field. So in particular, these two guys, Bjorn Sothman and Rafa Sanchez, we've been writing some uncountable number of papers together. Karine Leheur is an old friend of mine. We have some work together. And of course, Marcus connects all these people together. Cyril O'Ward is a new postdoc of mine that comes from Alexia Alfev's group in Grenoble. And then I just was amusing. So here we are drinking here, having some tapas in Madrid with Rafa. We were working together. This is in January and February. And if you look closely, it's appropriate. You have this little mirror picture there of me. And so there in Madrid, we were visiting the Prado. And so this is like a new Velasquez photograph there, right? Okay. Okay, so let's start with some motivation. If you take, almost everyone has in their pocket one of these devices, right, something like this, and you know that if you use this for more than about 30 seconds, it gets really hot, right? And so if you think about the thermal resources involved in building computers, they're up to the point now where these computer chips are generating so much heat they simply can't throw it away fast enough. They have to design all these absurd mechanical devices to try to dump heat out as fast as they can go. And I just mentioned this as a motivation, thinking about we have all this wasted heat that's being thrown away all the time. Is there any way, from a physics perspective, we know that's useful energy in some sense. Can we take that heat and begin to start thinking about how we could reuse that and recycle that energy? So the basic idea then, from a physics perspective, because this is a tutorial talk, I want to give some very basic background, is that if we take coal and we burn it, this is again what we do with our caveman era, we can become warm again, or instead of burning it, we can boil water and turn it into an engine. And so this is the basic motivation of heat as the resource. So what we're going to be doing, and similarly, we're thinking about the heat from our laptop or something like that. We can it'll warm up our lap, or we could use this laptop, harvest a portion of this energy to generate some useful work or electricity. And we could then, for example, do things like lower the laptop's energy consumption, or use this energy to run a sensor, or any kind of things like that. So that's really one of the motivations for this research, is to develop this kind of energy harvesting nano engines to be able to convert heat to electrical power or some usable work. All right, and so we all know about heat engines from back in our university days. So the most famous one is we have this kind of Carnot cycle working between heat baths going through adiabatic and isothermal paths in order to carry out useful work on this device. And so again, this is one example of such a heat engine, but it's not the kind we'll be talking about today, not the kind that has been discussed earlier in this meeting. So I want to give some historical motivation for this in the context of electrical circuits. So there's a really nice paper I found back that was written by Leon Brillouin back in 1950, and he had the following thought experiment. He said, let's suppose I have an electrical circuit that has, in principle, a battery, but let's just say a voltmeter in principle, and I have a diode here in my circuit, and I have a resistor, and the resistor has some temperature T associated with it. And we all know that the temperature will make the voltage across that resistor fluctuate just because of the fluctuation dissipation theorem, but the diode only lets electrical current pass one way and not the other. So why couldn't I use such a circuit to be able to rectify the ambient thermal fluctuations out of the environment and create myself a machine just from the thermal fluctuations of the environment? Okay? And of course, we know, if we think a little bit, we realize that can't possibly work, but nevertheless, it's an intriguing idea, and that'll motivate some of the other designs we talk about later on in this talk. Turning to mesoscopic physics, there are some really earlier papers that I think helped inspire us. So one of this is, I think, was discussed earlier in this conference, talking about this idea of Coulomb drag, where you imagine you would bias one electrical circuit, drive an electrical current through one, and that would then somehow drag the current through some auxiliary circuit that's electrically coupled to it. All right, so that's one of the historically interesting ideas. And then also we are also motivated by this paper that Rafa Sanchez wrote with Marcus back in 2011, where he imagined had a single level quantum dot coupled to some other quantum dot going through some sequential tunneling process, and then being able to rectify current through this upper circuit simply by heating the lower circuit. So this was also an interesting and motivating example. All right. So when we talk about thermoelectricity in the context of mesoscopic circuits, we can think about at least two different ways of them. So earlier in the conference, we were discussing about this kind of geometry, where you imagine you had some electrical load, you had a mesoscopic element, and you had a cold reservoir and you had a hot reservoir, and you were looking at for example, the electrical current that would be generated by this heating process. And the thing that we have to realize about this, so this is very handy if we want to do something like a thermocouple, to do a thermometer or something like that. But if you look at the currents flowing through this, you have both charge and heat currents flowing through the same in the same contacts. Whereas if we're interested in an application like energy harvesting, we have a source of energy we want to take the energy from and convert it into useful work, it's very useful and practical to think about this kind of three-terminal geometry where you can separate the heat currents from the electrical currents. So now the idea is in this geometry you have this source of energy that's coming from your cell phone or what have you that generates that will send heat energy currents through this terminal, but then the charge currents will be carried through this circuit that's now all at the same temperature. And this is very handy because when you try to do experiments in a circuit where you have different temperatures, you get thermal voltages that are produced, and it's very difficult to then unpack all of the source of the where the voltages are coming from what temperature source. All right. Okay, so this reminds me a little bit of a commercial I saw as a child back in the United States. This is from McDonald's. They had the scheme, advertising a scheme at one point where they had insulated packaging that would keep the cold side cold and the hot side hot. And it's this exact principle we're applying here to our mesoscopic thermal engine. Okay. All right. In those coming slides, I'll go through a lot of the papers that I've been involved with and mention some of the closely related ones. Both so for completeness, but also so I don't offend anyone else in the audience, I want to mention two different review articles that really go through in a lot of detail. So one was published by myself together with Bjorn and Rafa. This was actually done, this was 2014, but it already has been well cited in the literature, so I think this was a useful reference for many people. So this gives some summary of energy harvesting using quantum dots specifically. Much more recently, there's a very beautiful review article by Beniti, Casati, Saito, and Whitney. Many of these people are here, and give a really nice, thorough review about this area of mesoscopic transport and thermoelectricity, talking about mesoscopic conductors in particular. So I also would recommend this as a nice reference for someone that's new to the field. Okay. So here is a paradigmatic kind of conductor I want to talk about, and I want to walk through some of the design principles of this engines using this example. So the idea is this is a planar geometry, so there's a bottom plane and a top plane. The bottom plane, I imagine, is coupled to some ohmic reservoir here. It has some temperature, it has some chemical potential, it has some temperature. And that is only coupled not directly, not through any leads, there's no charge transport, but maybe through a capacitor, for example. There's some upper conductor at this upper level. And this upper conductor also has some connection to some ohmic leads. It's got some chemical potentials and temperatures. And the idea, the basic idea is we want to try to turn this into a thermal engine. We want to heat the bottom conductor and then be able to generate power through an electrical circuit that involves the top conductor. So this is the overall goal. And the first step of that is to generate rectification. So if I heat thermally, can I induce an electrical transport through the upper conductor? Okay, so that's the system we'll be talking about. So here are the three different ingredients we're going to need as a part of our recipe to make such an engine work, to get rectification out. So the first ingredient we're going to need is we're going to have different temperatures in upper and lower cavities. So unlike Brillouin's example that I was talking about before, having simply something at one temperature we know from general thermodynamic principles won't work, but we'll see that in more detail as our first ingredient. The second ingredient is we're going to need some kind of symmetry breaking. Even if we have all the other ingredients, but if we have left and right symmetry, then we simply can't create the necessary conditions to generate a current, because I can always invert the geometry about its central axis, and by symmetry arguments would not be able to create a current, because that would violate the symmetry of the geometry. And then finally, even if I have these two, but I only have a linear system, that's not going to work either. So I have to have some source of nonlinearity as well, together with these other ingredients, and only all three together working in concert will be able to make rectification happen. So I'm going to illustrate each of these principles in the geometry I just mentioned. Okay, so first of all, so we have to have different temperatures involved. So suppose I applied some kind of electrical voltages or something like that. I won't be able to generate any kind of rectification in the upper cavity, but if I were, suppose as a thought experiment I were able to this, that would allow me to generate some steady-state electrical current in global thermal equilibrium. It would be able, so if I applied some small electrical voltage, I could then generate electrical power with only one heat reservoir in violation of the second law. And then further conservation of energy demands some net heat current passing between these two cavities. But if there's in global thermal equilibrium, that will then spontaneously create one of them being very hot and the other one of them being very cold without any input power, so making a Maxwell demon. So these are some reasons why I can't do this with one temperature, even though if I look at these ideas from Brill-1, it seems suggestive that I may be able to. The second principle, this breaking of left-right symmetry of the leads, even if I have this temperature difference established, so this is this idea that if I can invert this geometry about the axis of symmetry, if imagine I had a current that was flowing from left to right, by inverting about the axis of symmetry, then it would go from right to left. But if that's exactly the same geometry, then that can only work if the current is 0. So by symmetry, then I can't have any current rectified, so I have to break the symmetry in some way. All right? And then the third ingredient is even if I have 1 and 2 together, I need to have some source of nonlinearity. Okay, and so this Brill-1 diode, it's a little bit like Feynman's ratchet and Paul he discusses in his lecture series. So you have to have this source of asymmetry or nonlinearity as well. Okay. So in our model, where does this nonlinearity come from? So I can get this nonlinearity in a variety of ways. In the model I'm talking about, it happens because in mesoscopic currents or mesoscopic conductors, the current or transmission of the context depends on the energy of the electrons that are transmitting through it. Okay, so if I have high energy, I'll be more transmissive, whereas if I'm at low energy electrons, I'll be less transmissive. And so here is the basic mechanism of the idea. So imagine these shaded gray lines represent the transmissions of the barrier. Say I have two barriers. One of them is more reflective at low energy and less reflective at high energy, and so on like this. And so the idea is that I send in electrons either from the left or the right, I can come into this central region that's, imagine it's hot. I can absorb some energy delta U from the central region. And then when I try to go out, for example, to the right, I see that I tend to be blocked on the right-hand side, but not on the left-hand side. And so then I'll be preferentially be transporting to the left. Okay, so this is the basic idea, the mechanism behind this feature. So this breaks both left-right symmetry. You see the barrier on the left is lower than the one on the right, but also has this nonlinear effect because of the energy transmission changing with it, the transmission changing with energy. Okay, so if I work this out, we can work it out using a simple model, which we did. I won't give you the details, but I'll just give you the result. And the result is very simple, but it has all these ingredients in a very simple way in a simple formula. So here is the average current you generate through that upper contact when I heat the lower element. And you see it basically has a few different ingredients in it. The first is the Boltzmann constant times the temperature difference. So again, I have to have a temperature difference to generate the electrical current. So this is the first important ingredient. There's a time scale. So a current is a charge divided by a time. So the charge is electron charge. The typical time scale here is just an RC time of the coupled circuits. So it's a complicated expression involving the impedances and the capacitances. We'll just give a simple RC time. It sets the time scale of the transfer. But maybe the most important thing is this other parameter, lambda, and this lambda incorporates these first two ingredients. It breaks the symmetry between left and right, and it has the nonlinearity of the energy dependences in it. So what it is it's the energy derivative of the conductances of the left guy and the right guy minus the antisymmetric combination. The derivative on the right guy times the conductance on the left guy divided by sum. And so you see that if either there were no energy dependence, if G prime were 0, for example, then lambda would vanish. Or if I had symmetry, if I had left is the same as right, this antisymmetric combination would also vanish, giving me no rectification. So all these ingredients then are present then in this final formula, but the ingredients themselves transcend this particular example. Okay, so that's one example. And then Okay, good. And so now that gives us rectification. But rectification is not enough to generate power. We want to make the current fight against a electrical potential. So we have to think about what's going on. So we're going to put in some heat into our system. We're going to generate some power with the light bulb. It turns out that you can actually calculate the heat current flowing through the system. It's also proportional to the temperature difference. But you see there's no added nonlinearities needed here. It's just the RC time. So if everything is symmetric or energy dependent, heat is still going to flow from hot to cold. The whole trick is trying to figure out how to efficiently convert that heat into something useful. Okay, and so we can calculate the power, so that turns out to involve the square of this nonlinear parameter and the square of the temperature difference. And so this is the maximum power you can then generate. And it turns out that if you put it, what you need to do is you need to put make this into a circuit, and you have some resistor that's driving the current is driving against, and you get maximum power when you impedance match, when the resistance of the circuit is matched to the impedance of the load. And so you get this result. Okay. All right, so what are the results of this model then? So this is an exactly solvable model. So the methods we use here, I'll just say a word or two about that, is we're using transport theory, but then because all the physics is driven by the fluctuations, we have to use some noise model. So we use Boltzmann-Langevin type of equations to be able to predict this. And it turns out that mathematically it's very tricky to do this, because if you don't treat your noise sources just right, you end up violating the second law of thermodynamics. So knowing exactly how to convert into the right stochastic calculus is very important to get this right. Yes, so it acts as some thermoelectrics. So I apply a temperature gradient and I generate electrical current. And then I can also, but then by applying some electrical bias, I generate some backflow of current. And I'll go into this a little bit later. But you see very clearly, if I apply a bias the other way, I get some backflow of current that will tend to cancel the thermoelectric current. But that's what generates your useful power. Okay, we get the impedance matching. We find that efficiency is generally less than the Carnot engine. This is not a particularly efficient engine, but it can still give much larger currents, for example, than if I look at the more efficient engines, like the quantum dot engines I'll talk about in a moment. You get a lot more current because you have many open channels in this kind of geometry than if you had, for example, sequential tunneling processes. Okay. So let's talk a little bit about experiments. There is a nice experiment published in 2015. This is by the Würzburg group. And basically they're able to make this energy harvester. So you have the same kind of physics there. This is now their little cavity. This is the quantum point contact 1, quantum point contact 2. You heat this central region, and you generate these kind of currents. So this is basically looking at the current through the blue channel as you change as you change a gate voltage here. And you see that this is the experimental curves that you tend to predict, and this is the theoretical prediction that you would also find. And maybe what's interesting about this experiment is that they maybe cheated a little bit, because they didn't actually heat this lower element. They just applied some very large amplitude oscillating voltage to it, right, to sort of mimic a very highly fluctuating temperature. But nevertheless, that mimicked this thermal excitation to generate these kind of curves. And you see that actually because they're able to do this, you've got relatively large currents here. This is in the nanoampere range, which is quite big for mesoscopic samples. Okay, so this was a nice paper.
What was the equivalent temperature of this?
Yeah, so the equivalent temperature was like 10,000 degrees or something like that for this particular example. But okay, fine. You're right. It's kind of funny. However, they also had this experiment was all published almost exactly the same time. This is by the Christian Glattli group in France. And here they did a little bit better with heating. So they actually did, so what they did is they heated this, so this is the sample. They heated this lower channel by applying ohmic, basically by applying a current through this lower channel, just using ohmic dissipation to heat up this region here. So it really was just creating a hot spot using currents. And then indeed, so this is now the capacitor. The capacitor is just these interlocking metallic loops. That's basically your capacitor, and that channels the energy flow then into the upper circuit, and then you generate a directed current through the upper circuit. Okay. And again, once again, we can compare the results of the theory. to the experiment. And so this is a color map here of the current as a function of they can change the transmissions of both the left and the right quantum dots by applying plunger gates to these guys. And as you dial through the transmission on the x and y axis of the QPCs, you find this color map of the currents. And so if you look carefully, so this is, you can't really see it, but this is now in the picoampere current range, which is maybe a little bit more similar to these mesoscopic currents events. And again, you see this kind of experiment, and this is a theoretical prediction for this kind of circuit. Okay? Good. Right. So this is really nice. However, there's some liabilities. And the liability, I list them here. So the first one is that we have to depend on these energy-dependent nonlinearities of the transmission. These tend to be typically rather weak nonlinearities. So we might say, what can we make them stronger somehow? If I want to generate more current, more power, what do I need to do? In mesoscopic conductors, this is typically a one-channel effect. So if I have a relatively open QPC, I already have N channels that are basically energy independent. But this is only changing one channel, so it's a relatively small effect on top of the background. And it typically leads to lower power than we would like and also lower efficiency. So is there a way of trying to make this better? So even though we can make this experimentally and do experiments on it, let's try to figure out and see, is there a natural way to zoom in on just one of this single channel nonlinearity and maximize that to our gain? And so this is, so that what we're going to do is we're going to use this idea of resonant tunneling in quantum dots. And so this goes back basically to a paper by Mahan and Sofo. I think they just talked about having this very sharp transmission feature, but you naturally get this with these resonant tunneling quantum dots. And here's a little cartoon of it. So the idea is that you have a quantum dot here with a particular energy level. And if the incident electron is detuned from that energy level, I get no transmission. But if I lower the gate voltage here on this quantum dot and bring the level into resonance with the energy, what happens is the electron then transports into this dot and is able to rattle around many times coherently and then come out the other side. So rather than having a sequential tunneling where I come in, I wait for a while, and I go out, I basically go almost immediately in the steady state through with a very high transmission if I'm resonant with this level. Okay? And this feature that I just described to you acts exactly like an energy filter. So it basically allows you to say, I don't want this electron, so that's detuned from this guy, so I throw it away. This one I do want because it is tuned, and I let it pass. So I'm able to very selectively take the electrons I want at that particular energy and throw the rest away. So here is a design that we came up with. And indeed, when I talk to people about if they want to know something about thermoelectricity, what I do for quantum engines, I show them this picture because anyone can understand this picture. I can explain this picture to a child of 9 years old. And so here is the idea. So the idea is, again, I have this two-terminal geometry. I have some cold ohmic bath on the right. I have some cold ohmic bath on the left. In the middle, I have some relatively large electron cavity. This is not a little quantum dot, but something big. And I imagine I heat this. So I connect this thermally to my source of energy I want to take from. And what happens is very simple. By heating it, it's at a higher temperature, so the Fermi function broadens much larger. It transitions from 1 to 0 on a larger energy scale. So this is energy in the x-axis. This is position in the, energy in the y-axis, position in the x-axis. And now what I do is I place my quantum dots with the resonant levels asymmetrically on either side. So the dotted line is the Fermi energy of the whole thing. The left dot, I put the energy level below the Fermi energy. On the right, I put it above the Fermi energy. Now what happens? I just told you, unless I'm exactly at this energy, I can't pass through this dot. Transport is forbidden. But if I'm at the energy, I can take an electron from the left side, I resonantly tunnel through this level, and I put the electron here on the right side inside the cavity. Now this cavity is hot, so I'm able to take energy through inelastic scattering from this hot reservoir. It raises an energy up to some distance, and now it tries to go back out to the left. But it's blocked. There's no channel out to the left. There is a channel to the right, though, so I can take energy from on this guy here, resonant tunnel to the right, and now what you see is that's the only possible processes in this system. I can't go really back because the energy level here is much smaller. So these levels are almost empty, so it's very hard to go back. So it's more empty than these are filled, and vice versa. The reverse process is also hard to do because this is mostly empty and this is mostly full. Okay? So simply by heating that central cavity, I then very naturally rectify current. I push current from left to right just by heating the cavity. So it's very simple, but also I think quite elegant. One of the interesting features is you see there's a special energy scale in the problem. If I take the difference of this energy and that energy, ER minus EL, that's the energy sort of gap, that's the energy gain function in this problem. And for every electron in a steady state that I push through this conductor, I have to gain exactly energy ER minus EL. So this is called the tight coupling limit, where I convert exactly that amount of energy into 1 unit of charge. So it's a perfect energy to charge converter. So because of that, if I look at the energy, the efficiency of the engine, so this is what I was talking about. Because there's this energy to charge conversion, if I drive some thermal heat current J through the system, I have to convert exactly into a charge current I via this conversion ratio, E over delta E. And so what you see there is that when you look at the thermodynamic efficiency of this engine, because the power is just the current times the voltage I apply across this current, the efficiency is very simple. It's just the voltage I apply divided by the energy difference. Formally, what we do to actually solve this model in more detail, we basically just do some simple things. We assume that we have some Lorentzian transmission of each dot. It's not actually a delta function. There's some broadening we take into account. We impose just conservation of energy and conservation of charge in the whole system, and that fixes what the temperature and the chemical potential of the central cavity are. Okay, and so then we assume that the heat is being transferred into this cavity at a fixed rate to keep this cavity at a fixed temperature that's hot. Okay. And again, the formulas turn out to be quite simple, so we can relate the heat current flowing in to some simple combination of Fermi functions given a chemical potential mu, and that we have a temperature Tr on the outside and a temperature Tc on the inside. Okay. Now what's interesting is I mentioned before, if I start applying bias to this, so I'm going to start flowing current from left to right. I want to make this run against a load, so I apply some voltage here, and that's going to start generating power, but it's also going to have a backflow of current because of the bias I'm applying on the right side. At some point, as I keep making that bias higher and higher and higher and higher, that two processes will cancel each other. So the thermal induced current will match the backflow from the voltage, and so I'll have exact equilibrium. So for every process I go from right to left, I'll have the same process equally probable going from left to right. And at that configuration, we call this the stopping configuration, where I stop the thermal flow of current, and that's exactly a Carnot-efficient heat engine at that point. Because at this point, everything is thermally reversible. I can go either, have this process like that, where I gain energy, but then I can also go back the other way, lose energy, so that's the condition where I have the maximal efficiency. But as we're hearing about earlier, that's also the case where I generate no power. So no power is produced, but I have perfect efficiency at that, perfect Carnot efficiency at that point. Okay, So when mu is delta E times the Carnot efficiency. Good. All right, so then we can do things like optimizing power, optimizing efficiency, optimize power at maximum, efficiency at maximum power. And so it turns out to do that, so here are some of the curves. So this is power versus the energy difference delta E. So this is maximum power. So you see that there's some sweet spot here. I want to make the energy difference to be about the same as the temperature. That gives me maximal power. As I start cranking up the temperature, obviously it's going to keep growing with delta T over T. And then when I optimize my parameters, I see that so I see typically that the width that I want to apply, if I want to maximize the power, is around the temperature, the order of the temperature. And the delta E is about 6 times the temperature. So that's how you optimize this system. Okay. Good. So that's the single engine. But now we talked about earlier, what if I wanted to not just create, a few nanoamperes of current or a few femtowatts of power, but I wanted to do something actually useful. I wanted to make this thing into some device that you could use with your laptop or whatever. How could you do that? So here are a couple of ideas that we had. So one idea is something we call the Swiss cheese sandwich. So the idea is that you have your cold layer, your two cold layers, and then you sandwich the hot layer, and you imagine putting some layer of quantum dots between these two regions, and the quantum dots may be, for example, self-assembled quantum dots. And you may put also an insulating layer as well. So you try to avoid the direct thermal transport that would tend to make these guys go into thermal equilibrium. And so then the operation of the device would be like this. You'd put in heat from some sources on the outside, and then the charge current would be flowing through the Swiss cheese sandwich in a different kind of electrical circuit. So this is one way that we've thought about trying to scale this up and make this into some device that would work producing a macroscopic amount of power.
How do you tune the levels?
Yeah. So what you would do is what you could do is you could do like a band gap kind of thing, or you could use like an edge singularity. They call these a Schottky barrier. If you put a Schottky barrier here, that would tend to lift the energy levels on the right up, down below. And of course, they won't be all exactly the same. There'll be some scatter, but we also studied this point, and we showed that even with some disorder in the position of the resonant levels, you still get good performance because the scatter is going to be smaller than the total energy difference on average. Good. Yeah. So then, just as an order of magnitude estimate, if you use this kind of geometry and I hook it up to a light bulb, so a square inch array of this kind of material would in principle produce about a watt of power with a 1 degree temperature difference. All right, so that motivates us to think about how could you make such a device and then be able to scale it up. So there are other ways we could do this. So other way that maybe be more practical is using an idea called a resonant quantum well. So this is, rather than the quantum dot that has a 0-dimensional shape, this is like a 2-dimensional device. And the idea now is that I have a cylindrically symmetric geometry I have a slice of this well of size L, and the idea is that this size L is then tuned to the Fermi wavelength of the transport electrons. And so the picture is now, again, that if I have this lowest level of the quantum well above this Fermi energy, I get no transport. But as I generate, if I lower the gate voltage, I bring it into resonance. I start generating current. I get lower and lower, and eventually I give it so low, and I go below the band edge, and then it stops producing current. So this is a simple model actually for making a diode, and so this is something that's called a Schottky diode. Right? So now we're going to try to use this for energy harvesting purposes. So the idea, this is something again we published with Rafa and Bjorn, is we have the same kind of geometry I talked about before, but instead of having a 0-dimensional device, you have this planar structure. And you put the lowest level, again, somehow below the Fermi energy here and above the Fermi energy there, and you can play the same kinds of games. So it turns out it's not as efficient as the quantum dot resonant tunneling geometry, but you can produce a lot more power, and it's scalable, right? So the bigger the transverse dimensions are, you get more and more channels, more and more power producing. So we get about 7% of Carnot efficiency at maximum power, but I get about 0.2 watt per square centimeter with a 1 Kelvin temperature difference. So this is really, I think, a promising kind of avenue to make a scalable mesoscopic type thermoelectrics. Okay, and then of course we can also go further with this game. So this is an idea I published with a student of mine in 2015. What if you don't just have one quantum well, but you stack them, right? So if you stack a bunch of quantum wells together, you make what's called a superlattice. So you alternate the properties. For example, you do like a gallium arsenide, gallium aluminum arsenide over and over and over again. What this does is this creates a mini band in your mesoscopic structure. So I think Rob, where's Rob? Is he around? You were talking about having this boxcar filter to do your maximum efficiency to given power. This isn't exactly the way that you would make such a boxcar type filter, because you have a mini band which excludes transport for certain energies, then you have a band that allows transport, then you have the mini band. So you broaden this into a sharp range of energies that you can get transport through and have it like this. So I should mention also, these are also really useful. So we heard about on the first day, that people don't often, they forget to talk about something important in all this, which is you have phonons as well. And the phonons are this parasitic channel of taking heat from hot to cold without having it do any nice work for you. And people always tend to sort of sweep this under the rug. But this is, of course, a really big problem. And so you have to solve this problem to make a practical thermoelectric. But these superlattices, actually you can study the phononic band structure of those as well, and those tend to inhibit the phonon transport. So this could also be a good way of then inhibiting phonon transport as well. The other example about the self-assembled quantum dots, that gives you some disorder, which also tends to scatter phonons. So that's a good way of trying to kill them as well. All right, good. Yes, okay, so now I have the privilege of being able to announce some unpublished experimental results. So we started working with the Charles Smith group in Cambridge. And this is so they wanted to realize this resonant tunneling quantum dot engine. So this is the sample that they created. So this is a false color image, but the hot cavity we have is here. We have the two resonant tunneling quantum dots are here and here. And you have these little plunger gates to be able to control them and also have current flow in and out through these channels. And so what they do is basically they implement our proposal by then heating this channel. So they apply some AC voltage here to heat up this hot region. And that then leaks, there's an open channel that leaks in here, and so that heats up this central region. Okay? So that's the source of the energy that we're now harvesting. And so that will then, by this mechanism I was just talking about, drive current between this particular current sample. Okay? And so here are the experimental results. So this is a plot of the current. This is the thermal voltage that you produce through the circuit, as well as the power you produce. So you make this current fight against a load. This is where you're generating your power. You're powering a light bulb or something like that. And so you can plot these as you vary the position of the left and right plunger gates while applying this heating. Okay? And so you see basically where you're getting these dots, that's where your resonant levels are coming into play, and then generating the power according to the mechanism we were talking about just a little while ago. Okay, so hopefully this will be on the archive in a week or two. I think we're finalizing the paper now. Okay, let me talk about some new directions in this field. So I think the other day, Linnea Archea talked about these quantum Hall ideas. So this is some of the work that we're also very interested in. And the idea was initiated by this idea of trying to build a quantum Nernst engine. Now, what is a Nernst engine? The idea is that you now have, in principle, 4 leads, and you want to heat 2 of them to drive the heat current through the hot and the cold. But in the process, you also now apply a magnetic field. And the magnetic field classically will then curve the electron orbits like this. And so that will then tend to drive a current then from this lead to that lead. So the Nernst engine uses the magnetic field to then drive a current using a temperature gradient. So what we were sort of motivated by this paper by these guys that did a classical version of this. And so what we wanted to do is, so what happens if you turn the magnetic field up really high? Well, then you get driven into the quantum Hall effect. So now in the quantum Hall effect, you don't have this sort of mesoscopic usual transport. You have chiral edge channel transport. Everything is carried along the edges. It's a really cool area of physics. So now the current doesn't go like this. It has to go along the edges like this and go around like so in this chiral way. So we proposed some initial quantum Nernst engine using either this quantum point contact. So remember what I told you about heat engines. The same principles are true with this engine as before. I need a temperature difference, I need to break the symmetry, and I need nonlinearity. The nonlinearity comes now from these quantum point contacts that have an energy-dependent transmission here. Or we could do something like this. We could put an antidot in the middle here where I could have now orbits that go around this antidot or scatter between edge states like this. So either one of these will work and then realize this quantum Nernst engine. I want to spend more time on another geometry that we published. So this was a Europhys letter. We published also this paper, which I really like this paper a lot. This is now a 3-terminal device, but it has very nice features. So let me describe a little bit the features to you. So I have 3 terminals. I have quantum point contacts on all 3 in principle. I heat one of them. So let's heat up the top one. And what I want to ask is, what's the thermoelectric response of this device? Now, you would think people have been studying the quantum Hall effect for decades and decades now. You think this is all done, but no, this is all new stuff. People just didn't think about thermoelectric transport, or not at least in this context. There's something really cool that happens. So suppose, for example, that I apply, I pinch off my plunger gates here on either this one or that one, depending on how I apply the magnetic field. Now what happens is if I heat this gate like so, what's going to happen is that I'm going to create essentially electron-hole type pairs. I'm going to broaden my Fermi level, and they're going to all come along this channel and all just be dumped here. Okay? But now, if I do the same thing, and now I put a plunger gate here, and I have a quantum point contact, now I have these excitations, electron-hole pairs, coming off of this hot geometry. And now what happens is that this is going to sort them. It's going to send the high-energy electrons. That's going to make it through the quantum point contact and go there. The low-energy ones are going to be reflected off this guy onto this channel and go there. So now I've got the electron-like excitations going to the left. The holes go to the right. I generate electric current. It's extremely simple. But it's so beautiful because if I ask, basically if I ask about, so this is the Seebeck effect, right? I heat and I generate electrical voltage. But now I can ask about the Peltier effect. What if I do the reverse? What if I apply voltage? Do I generate heat current? It turns out in this geometry, there's actually no Peltier effect at all. So I can completely separate the Peltier effect from the Seebeck effect using the chirality of the transform. Okay, so I give a little summary here about this. Good. And so, but it's also what's interesting is that you can see I can transform between these different geometries by either doing parity flips, by flipping around the axis of symmetry, or by changing the sign of the magnetic field, going from into the board to out of the board. And remember what I told you before, I need to break the symmetry somehow. So before I was using breaking the left-right symmetry using the fact that the transmission of the left was different from the transmission of the right and the energy dependence. Here I simply use the magnetic field to break the symmetry, because it breaks time reversal symmetry. So this is really the key now to understand these new thermoelectric effects. All right, so this is the way I like to think about it. Usually in thermoelectric response, I write the electrical current and the heat current in terms of this linear response Onsager matrix, in terms of the affinities of the voltage and the temperature. Now usually we'd say that this is related to the charge conductance, this is related to the thermal conductance, this is the, basically like what is this? This is the Seebeck effect, I heat and I generate current. This is the Peltier effect, I apply voltage and I get heat, right? So normally these are two sides of the same coin. If I get Peltier, I get Seebeck, right? But by introducing this chirality, I'm able to divorce these two guys from each other. I'm able to let this guy be something big and this guy go to 0, or vice versa. So this is something that I don't know of any way of doing within classical thermoelectricity. Okay. So this gives another way of thinking about the other way around. If I apply voltage and then figure out a way of getting the heat, you can read it. I'm not going to go through the whole thing. But there's a simple way you can understand it just by using the fact that this quantum point contact serves as an energy filter. So basically it filters the hot electrons and the low electrons together with the chirality of the motion, explains all of this. Okay. Good. We can also think about heat management with this kind of geometry. If I think about not just thermoelectricity, but heat management, like a heat diode, how do you make a heat diode, for example? This would be, so electrical diodes, I apply voltage one way, I get current. I apply voltage the other way, I don't get current, right? So the heat diode is exactly the same thing. I thermally bias one way, I get a heat current. I thermally bias the other way, I don't. And it's really simple to see how that happens, right? Because again, the chirality of this motion, again, if I have something like this, if I flow one way, I just dump out into this way. But the other way, I have to go through this energy filter. So you can use this as this heat diode and calculate this rectification coefficient as the ratio of the antisymmetric combination of the heat Onsager response. And what you see is that when I plot this on a logarithmic scale, you get very nice, very sharp transitions, again applying, using this chirality of motion to really distinguish sharply between heat flow in one direction from heat flow in the other direction. All right. Good. So let's talk about another new direction. How am I doing on time, David? Sorry.
10 minutes.
Okay, good. Here's another new direction. So this was the one that mentioned by Rosa Lopez the other day. we can think about another way of breaking symmetry in this system. So we've talked about using the geometry to break the symmetry, using the chirality, the magnetic field, to break the symmetry. Here's a system that's perfectly symmetric in its electrical properties, but I break it using asymmetry of the electromagnetic environment. So what I imagine doing is I have, for example, a quantum dot with a single level. It's Coulomb blockaded. I apply voltages across that, but then this guy is not in isolation. It's connected to some electromagnetic environment modeled by some impedances. Okay? And I can imagine I can heat one of these impedances that couples to this quantum dot. That's one kind of geometry. Or I can heat the leads. The electron leads can be hot and the environment can be cold. Either one will work. And now, you can see that something interesting happens. If I had only energy conserving reactions or transition, I wouldn't get any current at all. But what can happen is that if the level is above the Fermi energy of the leads, I can do transport by taking photons from this environment. So I quantize this electromagnetic environment, and it can provide me photons to be able to absorb and take the energy up into this higher level, absorbing energy from this device. Again, we're talking about heat engines here. And then it can go across and transport to the right side. And the similar thing happens here. I can be at a high energy electron. I can give energy. I can emit a photon into the environment. I can come down resonant with the level and then come down again, giving off more energy. Okay? So the way we solve this kind of model, Rosa talked about this in great detail the other day, so I won't repeat that, but it's using this P of E theory that takes into account the fluctuating phases of this environment and how that affects the tunneling transport of this quantum dot system. And what you can do, this is just the result, you can calculate, for example, the current that you get as a function of the position of the dot level relative to the temperature, and you see that you have these kind of, again, it's these nice curves, and what you want to do to maximize your current is you basically want to say, I optimize the sweet spot of my energy to my temperature, and that's going to be able to take the most from the environment that is allowed. Okay? And the equations are also nice. They're reminiscent of the equations I showed you just a little while ago. So the current has this antisymmetric form, basically in terms of sequential tunneling, two tunneling to the right minus two tunnelings to the left, where these tunneling things are some horrible combination of digamma functions. But the interesting thing is that your coupling to the leads, the coupling to the electromagnetic environment, is quantified through these alpha parameters. That tells you what the resistance of your impedances is relative to the quantum resistance. And you see everything is antisymmetric in that parameter. So even though the electrical degrees of freedom are perfectly symmetric, it's this coupling to the quantum vacuum that's asymmetric. So we call this a quantum vacuum engine. That provides the nonlinearity that drives the engine. Okay. All right, so in my last few minutes, I want to tell you about something new. So far, and indeed this whole conference, we've been talking about quantum generalizations of this guy. You're burning coal or something like that, and you're trying to convert the coal to do something useful. But of course, our technology has evolved since the steam age. Now we have fancy Porsche cars with internal combustion engines. So is there something that we can make a similar kind of quantum shift in our resources? I want to think about, can I design a fully quantum engine that operates with no thermal reservoirs at all? We kick the thermal reservoir out the door. And we want to ask, furthermore, can I do an engine that has no work done at all by the system Hamiltonian? So the system Hamiltonian does no work. Is it possible to do this? And our central claim is that yes, this is possible to do this if I think about quantum measurement as a resource. So this is the idea. We're going to think about quantum measurement as a resource, and it's pseudothermal in the sense that it's stochastic. I can't predict the results ahead of time, so it has some similarities to heat, but it has a lot of differences as well. And one of the big differences is that because there's no thermal environment, there is no Carnot efficiency. You can get around the Carnot efficiency because you're not working with thermal environments. So here are two examples we talk about. We talk about trying to lift a single atom up an elevator, to design an elevator that lifts a single atom up a floor or two, or to charge a battery using a single electron. How would I do such a thing? So the idea is the following. So suppose I have my platform, elevator of my platform sitting here like this. And my task is I have a counterweight here so that the weight of the platform is balanced by the counterweight. But then on top of that I put a single atom. So the single atom tries to push this down. And now I want to lift the single atom up, say 1 meter, and doing some work. And then I can repeat that to make a cycle. So how do I do this? So here's what we propose to do. You have your atom sitting here on a piece of paper. We let it go in the ground state, so it's sitting here localized, just doing nothing. And now I come along and I ask, I do some kind of measurement. Okay? Now if I just ask, where is the electron? We know from quantum mechanics that we'll get a definite answer. The electron is, or the atom is here, but then the quantum mechanics tells us I then have to localize my wave function to a delta function at that point. And if I think about that for just a moment, I realize if I localize the wave function to a delta function, that takes an infinite amount of energy. So that measurement is actually impossible to do from a thermodynamic perspective. So I do something more gentle. I simply say, is electron within some distance epsilon from the bottom of the elevator? And it turns out that that measurement is also infinitely costly because that introduces a discontinuity and a kink in the wave function, which is also costs an infinite amount of energy, which is also impossible to do. But I can do something a little bit more gentle than that. I can smooth it out and I can say, I design a measurement that tells me if it's not here, it'll give me a click, but it won't tell me for sure it's up here. I have to have some transition region. So the measurement will have some smooth crossover from epsilon to epsilon plus w, and so it'll tell me for sure it's not there. It's probably here, but it may, with some shading region, be in the middle. Okay, so this is our sort of fuzzy measurement we're going to make. That's step one. Step two, here let's go to the steps. So this is my step one. So I'm going to design an engine. Here's my 3-stroke engine. Step one is I make a generalized position measurement. Step two is I do some feedback. If I find the atom is not close to the wall, I then use my counterweight to move the elevator up a little bit, and then stop when I reach epsilon. If it is there, I just wait. Okay? In either case, I wait, and I let this atom emit a photon or whatever. I relax back down to the ground state, and then I repeat this process. So this is my engine. So this repeats this process, and then now eventually the elevator is going to go up, 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 up like this. Okay. So you can analyze this using quantum mechanics, figuring out what the efficiency of this process is, how much work that you do. And what you find is that it depends on how you change these parameters. So this epsilon parameter, how far I look away from the wall, and this w, how much I smooth, that will then fit, I can calculate the efficiency. And what's really cool is that if I set at a particular value epsilon, and I dial up my w large, 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 I see my efficiency gets bigger and bigger and bigger, and eventually reaches 1. So I can have a perfectly efficient engine using quantum measurements. Now, many questions are then suddenly raised by this, what I'm telling you. So one question is, where does the energy come from? Right? And the energy comes from the process of the measurement. So if you go through the analysis of coupling to some meter to actually do the measurement, to figure out how am I doing this, the point is that the way I'm coupling, the thing I'm coupling to, doesn't commute with the Hamiltonian. The Hamiltonian is just p squared over 2m plus this potential, and so I'm making a position measurement which doesn't commute with it, so therefore the energy and the thing I'm measuring are not commensurate. And so what's happening is that somehow the measurement device is giving energy to the system. So that's actually my resource. The resource is the energy that I power the measurement device with. I have to reset the measurement device. That gives it the fuel, and the fuel is then converted into this machine. And then furthermore, I can also look at how much work is produced, and there's a sweet spot for the work, and as I go up, the work goes down, 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 down. Okay? And the reason it becomes very efficient, it turns out that if I design this measurement right, I have to do a designer measurement, then what happens is that if I fail, or if I succeed, the measurement wave function gets disturbed, and I can see that the disturbed state, it turns out to be almost the same as the ground state of the newly advanced wall position. So it's because the fact that the wave function is almost the same as a new ground state, that means there's very little wasted energy in the waveform, and so I can simply keep going with that. Okay, good. So that's sort of my motivation to where I'd like to see kind of the field going. this is a whole new way of designing an engine. There's no thermal resources. It's a different kind of legitimately quantum resource that we're using here. Okay, so this is my conclusions. So I talked to you, I gave some general review about motivating energy harvesting from thermal wasted energy. We talked about how to design heat engines. So I gave you some 3 operating principles. They have to work between different temperatures. We have to break the symmetry somehow, the left-right symmetry, and we have to have some nonlinearity. All these ingredients need to be there. And I gave you several different examples of that. We talked about, and so what's also cool about these engines is that there's no moving parts in these engines. These are just autonomous engines. You just apply the temperature difference, it just starts working, right? That's something very different from our usual concept of an engine. We talked about experiments. We talked about ways to make it practical, and then towards the end, I also talked about some new directions in thermodynamic physics using quantum Hall effect, quantum vacuum fluctuations, and finally quantum measurement. So thank you very much.